Let's explore how the paradigm of agentic AI can be used to add value to the domain of data. As part of the agenda for this demo, we will define the paradigm of agentic AI. Next, we will explain the 4 popular design patterns in agentic AI. Finally, we will cover the features of this application which can deliver value for the data domain. Large language models, or LLMs, generate output in a single shot, whereas agentic AI systems can pause, review, revise, and iterate over their output. This iterative approach ensures that the results are more accurate and aligned with specific goals. There are 4 popular design patterns of agentic AI. 1. Tool use. This pattern allows AI to access and utilize external tools, such as databases or APIs, to enhance its capabilities. 2. Reflection. Reflection enables the agent to pause and reassess its progress, ensuring more accurate and high-quality results. 3. Planning. In this pattern, the agent creates a structured plan before executing tasks. This ensures efficiency and better management of complex workflows. 4. Multi-agent. Here, multiple specialized agents work collaboratively to solve a problem. This distributed problem-solving approach leads to faster and more scalable solutions. Agentic AI can address challenges in data engineering, big data, business intelligence, predictive analytics, data quality, and data privacy. Here's a quick demo of these capabilities. This is a demo of agentic AI for data. Let's list all the available database connections using the following prompt. What are the available database servers? The database connections that are currently available for this demo session are MySQL, Postgres, and Starburst. Natural language interface to query SQL databases is another popular requirement. Let us select a curated database called Agentic AI. This database schema is based on a mortgage management system and has 10,000 records of customers. The Spark engine is being initialized. To verify if Agentic AI has been set as my current database, I simply ask, please show me the current selected database, and it confirms that Agentic AI is the current database. We can perform a natural language to SQL query. I'll ask a question. How many customers are available? The table name is not specified, but the agent still identified it correctly, showing a total of 10,000 customers. In the right section, the Spark engine hasn't been initialized yet. The answer came from the SQL engine, not Spark. Once Spark is fully initialized, future queries may get processed through it. To verify this result in the actual database, SQL query generated by the agent is executed, and it shows 10,000 entries in the customer table, matching the agent's response. Let us now look at the capability of multi-model large language models to interpret images. Here is an image of a hand-drawn entity relationship diagram. Using Agentic AI, we were able to invoke the multimodal large language model's image interpretation feature and generate the data definition language, or DDL script, for it. You will also notice that there is a console on the right-hand side that gives you a chain of thought reasoning for this particular workflow. Agentic AI relies on the chain of thought reasoning to iterate over the output of the LLMs, which tends to improve the output quality significantly. In this product, it is possible to execute the DDL script and create the necessary tables in the database. This workflow is executed when the Run button is clicked. On the right-hand side panel, the chain of thought output is displayed. A temporary database has been created, ending with 1104, and we will verify this in our backend MySQL database server. Upon refreshing the MySQL database server, a new database has been created ending with 1104, and all the tables related to the mortgage management system have also been created. The 4 key tables are customers, mortgages, payments, and properties. As you can see, all the tables have been created successfully. This application handles challenges with big data, namely large-scale synthetic data generation, data virtualization, and orchestration using tools like Pandas and Spark. In this segment, the synthetic data generation capability will be showcased. Synthetic data generation is a popular requirement, but there is a limitation on how much data can be generated using large language models. This is due to the response token limit of LLMs. This limitation can be overcome, and we can support a virtually unlimited amount of synthetic data generation. This is possible using a two-step process in Agentic AI. In the first step, we create a Python script that has the logic to generate the data conforming to the database schema of the mortgage management system. Here is a custom prompt meant for the mortgage management system, which captures all the relationships between the data. In the second step, we execute the Python script, which populates the database with the synthetic data. Upon refreshing the database, we can see that the synthetic data generated has indeed been stored in the database. Many enterprises have their data estate distributed across Postgres, MySQL, MongoDB, Teradata, etc. Data virtualization is key to unlocking value in enterprise data, known as data virtualization, which is being utilized through a simple prompt in the Trino data virtualization tool to determine the number of customers. The client interacts with Starburst, which serves as a virtual database layer. Behind the scenes, several processes are taking place. If observed, the databases inside MySQL Server are available. A wrapper is being created over the actual database using Starburst. This includes the GCP virtual database, where catalogs such as Hive, MySQL System, and TPCH exist. MySQL, one of the catalogs, contains databases that are referred to as catalogs within Starburst. Inside this catalog, multiple databases are present. A query was made to determine the number of customers without specifying which catalog or schema should be selected. The agent was intelligent enough to identify the correct catalog and schema, write the appropriate query, and execute it. Upon execution, the query returned a result of 10,000 customers, demonstrating the effectiveness of the federated query written by the agent. Next, a more complex query will be attempted. The prompt instructs the Trio data virtualization tool to fetch details of 5 customers who defaulted on mortgage payments, displaying the response in a table format. The Trino client was initialized, and the system scanned the databases, ultimately writing a federated query. This query successfully joined the tables between customers and mortgages, fetching the required details. Upon execution of the federated query in the virtual layer, communication was established with the actual database, and the same information returned by the agent was confirmed through the data application. This demonstrates the accuracy and reliability of the federated query generated by the agent. Let's now explore another feature of this application to query big data using a Spark cluster. We will also observe the Spark queries being executed in the background directly on the Spark cluster. A query has been prepared to fetch the details of any 5 customers who have defaulted on their mortgage payments, with the table names specified. The process will be examined in real time, and the tool for the current operation has been enabled, while Spark has already been configured by the initialization of the SQL engine. As the demonstration proceeds, the exact query executed behind the scenes and the complete prompt used will be shown. The query execution will now be demonstrated by switching to the Agentic AI environment. The SQL from the execution on the Spark cluster can be modified to run on the MySQL server to validate the results. We can see that the output from Spark and the output from MySQL are identical. This application can be used for visualizing data and explaining the visualization generating business intelligence to support decision-making. A key feature of Agentic AI for data is its ability to automatically generate visualization strategies. Let's imagine you are working with a specific database within your organization. In this example, let's select the Agentic AI database. Once the database is chosen, the application will provide all the relevant visualization strategies for this dataset. In traditional scenarios, if someone lacks domain expertise or if a data engineer is unfamiliar with the dataset, they would need time to analyze the data before coming up with an effective visualization strategy. This application can intelligently analyze the selected database and automatically suggest the appropriate visualization strategies. For instance, it may recognize that a bar chart is suitable for showing customer distribution by industry, displaying the number of customers in each sector. The application generates multiple types of charts and offers recommendations on the best visualization strategies, making it much easier and faster to derive insights from your data. In this segment, let's explore the application's capability to generate visualizations. After generating the visualization strategies, the application can render the visualization using common chart types like pie charts, bar charts, and line charts. For example, let's create a pie chart to visualize the data distribution of the mortgage status. The pie chart will show the distribution of the mortgage status across different categories. Behind the scenes, the system generates a Python script. This Python script is responsible for rendering the chart. In this example, the pie chart displays two mortgage statuses, default and active. According to the chart, default accounts for 14.3%, while active makes up 85.7% of the total. If we want to derive business insights from this visualization, we can use a prompt to request an explanation. The explanation reveals that the majority of mortgage accounts are being actively maintained. Only a small portion of account holders are defaulting on their repayment. This pattern suggests a stable financial situation for most account holders. The explanation provided will help the agent extract key business metrics and propose actionable strategies. As observed in the pie chart, 85.7% of accounts are active, while 14.3% are in default. The application generates key insights to mitigate risk and also to improve business metrics. The following points are noteworthy. 1. Strengthening credit assessment processes to identify high-risk accounts early. 2. Implement or enhance early warning systems to mitigate potential defaults. Key business metrics, such as customer experience, can be improved through targeted investments in technology, increased marketing efforts, and regular portfolio reviews. By leveraging these insights, the organization can better manage risk. Predictive analytics features like time series forecasting and anomaly detection are supported along with explainable AI. The framework is extensible and can support many more such capabilities. The predictive analytics capabilities of this application will now be demonstrated, specifically focused on time series forecasting. A prompt will be provided to generate the forecasted loan amounts for mortgage data every month. The forecasting can also be adjusted to produce results on a yearly or quarterly scale. The tool's time series forecasting feature will be invoked, utilizing the neural profit library to perform the predictions. Progress will be monitored as the forecasted loan amounts for the next month are generated. Forecasting can also be extended to cover one-year predictions, with additional metrics such as mean average percentage error available for further analysis. Moreover, the model's performance can be evaluated in greater detail, including aspects such as training loss, regression loss, mean loss, and epoch-related metrics, allowing for a comprehensive understanding of the forecasting process. Another example of predictive analytics is anomaly detection. In this example, anomaly detection is implemented using the isolation forest algorithm. This is invoked using the Agentic AI application. A prompt is created to identify the anomalies, with the output displayed in tabular format. As the predictive model is invoked, the anomalous data entries are identified, along with additional details such as the anomaly percentage, confidence score, and status. Furthermore, explanations for why specific records have been marked as anomalies can be obtained. As an example, a prompt will be taken as input to explain the anomaly in the second row of the output. Similar requests can be made for other rows in the data as well. The provide anomaly explanation tool of the Agentic AI is then invoked, and the underlying details can be observed. Let's try to understand the explanation for a particular example of an anomaly. In this example, the credit score of 328 is flagged as significantly low by the system. Additionally, the loan's stated purpose is for a vacation, which is typically regarded as a non-essential expense, raising a red flag. The employment history provided is also vague and lacks sufficient detail, leading to concerns about the applicant's job stability and reliability. Thus, the anomaly detection capabilities and associated explanations are demonstrated effectively. The last segment of the predictive analytics capabilities to be showcased would prediction of loan defaulters in the mortgage database. The task involves identifying which 10 columns are most important for predicting loan defaulters. The database is first selected, and once the appropriate database is determined, random forest model is built to calculate the feature importance. The resulting feature importance metrics are displayed, including details such as the number of days employed, along with the importance of each feature and their corresponding confidence scores. Next, the prediction of loan defaulters will be performed, along with explanations for the top 5 predicted defaulters. As this process unfolds, the question, thought, observation, action chain of thought can be observed on the right side of the window. The prediction results include the mortgage ID, explanations, and other relevant details. For instance, an example result indicates that customer ID 5770 with property ID 5770 is predicted to be a defaulter on the loan with a 100% probability. The occupation type is identified as labor, which may suggest a lower or unstable income, thus contributing to a higher risk of default. Additionally, since this is a supervised machine learning problem, a confusion matrix is provided after the training stage, indicating true positive observations of approximately 24,669 and true negative observations of 2,589. Further evaluation metrics such as accuracy, precision, recall, and the F1 score are also made available. An F1 score of 99.2% indicates a high accuracy of the predictive power of the model. Maintaining high data quality is critical. Record-level entity resolution is an important feature to ensure data accuracy, consistency, and completeness, which is vital for any downstream analysis. A significant feature of this application is entity resolution at a record level. Records in a table can be ambiguous, and there is a need to perform entity resolution at the record level. A single customer can have multiple entries across various tables in the database. For example, 2 records might appear to represent distinct individuals, such as 𝗦𝗽𝗀𝗀𝗀 and 𝗦𝗽𝗀𝗀𝗀. Upon closer inspection, it can be observed that the 2 records share identical last names, date of birth, professional details, industry, email, and even phone numbers. The only noticeable difference is a slight variation in the name. This is a simple and effective technique to detect duplicate entries. Tools for data privacy prioritize protecting sensitive information by masking personally identifiable information, PII. This ensures compliance with regulations and helps maintain user trust while working with data. Now, another important feature of this application will be explored: personally identifiable information PII analysis. This feature is designed to help analyze and protect sensitive personal information within a dataset. Behind the scenes, the relevant function has been invoked. To accomplish this, a prompt will be used to mask the PII data in the customer table and display a sample of 5 rows. Once the tool for PII analysis is invoked, it can be observed that the names have been masked. For example, a name like Linda Becker is masked. Similarly, other personal details such as addresses are also analyzed and masked, ensuring data privacy. This approach allows the data to be protected reliably. Thank you. You can find out more about our business and tailored tech solutions at info@𝗦𝗽𝗀𝗀𝗀𝗀com or media@𝗦𝗽𝗀𝗀𝗀𝗀com.